Okay, so the last of our concepts that we need to move from 2D to 3D space is the idea of a position vector. So we saw in 2D space, if we have our 2D Cartesian space with an x-axis, an origin, and a y-axis, we said that a 2D position vector is a very special type of vector because unlike any other vector that's free to float around our Cartesian space, a position vector is locked in position because it always starts at our origin. So if we have a position vector, it's going to be locked in a certain position because it starts at the origin. And we know that because a vector will have a specific direction and a specific length as dictated by its components, that a position vector is a very specific vector. And we also saw that the endpoint of that vector, the point that the vector reaches, which we could say is the point P with the coordinates x, y, we said that the endpoint of that vector, the coordinates of that point, are equal to the components of our position vector. So if our position vector was lowercase p with the components x, y, then the point at the end of that vector is also going to have the coordinates x, y. And the reason for this is quite simple. If we're starting at the origin and we're travelling x units in the x-axis, then the coordinate of that endpoint is going to be x. And if we're starting at the origin and travelling y units in the direction of the y-axis, then the coordinate of our endpoint is going to be y in y. So it's quite simple and quite obvious. And we saw that position vectors, because they are a special case and because they are locked at starting at the origin, they're quite useful. And the first thing we saw them being used for was to define how we can find a vector that goes between 2 points. Now in later videos we're going to see there are further uses. There are actually a lot of uses for position vectors, and we're only going to scrape the surface in this DVD of how useful they are. But we're going to see that there are more uses for them. But in this video I'm interested in what happens if we have a 3D position vector. Well, a 3D position vector is no different than a 2D position vector. It's a vector that exists in three-dimensional space, so it's going to have an x, y, and z component, but that vector is locked in space. It's not allowed to float through that Cartesian space. It's locked in space because it must start at the origin. So just like our 2D example, our 2D position vectors, our 3D position vectors, and I need a little bit more space. There we go. Our 3D position vectors, if we had an x, y, and z axes with an origin here, a 3D position vector is going to be a vector that is again locked in place because it starts at the origin. And we know that our 3D position vector, if it was a vector p, because it's a 3D vector, it's going to have an x component, a y component, and a z component. And just like with our 2D position vectors, because we start at the origin and travel x units in x, the endpoint, which we could call capital P, is going to have that x component as its x coordinate. They are one and the same because of the fact we're starting at the origin. Likewise, if we start at the origin and travel y units in y, the y coordinate of our endpoint is going to be our y component. Again, they're one and the same. They're the same value because we start at the origin and travel y units in y. By the very definition of our vector, this is how far we're traveling in y, and we know because it's a position vector we start at the origin. Finally, because we're traveling z units in z, again starting at the origin, the z coordinate of our endpoint is going to be equal to our z component. So you can see it's the exact same thing as we had in 2D. Our vector is locked at the origin, and the coordinates of the endpoint are equal to the components of that position vector. We have the exact same thing in 3D. The only difference is that our vector and our endpoint exist in 3D space, and that means they have a z component. But other than that, it's the exact same thing. Our vector is locked, starting at the origin, and the coordinates of the endpoint are equal to the components of the vector. So we have the exact same thing, just with that extra z component. Now, one of the things we saw in the 2D position vector video was how we can use position vectors to find a vector that travels between 2 points in space. We can do the exact same thing here with our 3D vectors. So if we had, and I'm going to clear some space here. So if I was to reuse my axes, bear with me a second. Fantastic. So if I had 2 points in 3D space, and if this was, I don't know, a point that I'm going to name as S, and this was a point that I'm going to name as E, and I wanted a vector that travels between these 2 points, so a vector V, where S is the start point and E is the end point, we could find this vector by representing the start point and the end point using position vectors. So if I created a position vector that must start at the origin and travels from the origin to S, I could call this position vector the vector S. This is a capital S, this is a lowercase s. Again, the convention is the same whether we're dealing with 2D or 3D. We tend to, if we have a letter, a capital letter for a point, we have a small letter as the vector name for the position vector to that point. That just seems to be a convention in maths textbooks and the likes. So we've got our position vector S. Also, if we have our point E, we could define a position vector E. Again, this vector starts at the origin and travels to the point E. Then we know that we could find V, just like in our 2D example, by travelling from the point S to the point E. So if V travels from S to E, that's the same as travelling down the negative vector S, so negative S, and from there travelling along in the direction of E. So if we rearrange this, we'd get E minus S, and you'll notice this is exactly the same as we saw in the 2D case, that our V is equal to the position vector of the endpoint minus the position vector of the start point. The only difference here is the vectors in use in this equation have 3 components. They have an X, Y, and Z component, whereas in our 2D case, they just had an X and Y component. But in terms of the vector equation here, V is equal to E minus S. It's the exact same equation. So there's really nothing more involved with 3D position vectors than 2D position vectors. They're the exact same concept. The only difference is they exist in 3D space. However, I am going to set just one simple question that practices using our position vectors to define a vector that travels between 2 points in 3D space. And not only is this question going to help with practicing working with vectors, working with vector equations, and also working with position vectors, it's also going to prove, through being able to analyze the diagram and analyze our result, we can actually prove that indeed this does still hold true for the 3D case. So I'm going to set a question. And I actually want to set the question reusing this diagram to save me drawing my axes. So I'm going to erase everything we've got here. And this is the only question that I'm going to be setting for this video. Fantastic. So this question, which is, as I fill in the little bits we erased, there we go, question 1. I'm going to say we have 2 points in our 3D space. I'm going to say we have a point here, which I'm going to call point A, and I'm going to say this point is, let's say this is 4 units in X, minus 1 unit in Y, and 6 units in Z, say. And I'm going to say we have another point up here, which I'm going to call B, and let's say that B is, let's say 6 units in X, 8 units in Y, and minus 2 units in Z, say. And what I'd like is a vector that travels from A up to B. So the vector V is a vector that travels from A up to B. But I'd like you to find V by using position vectors. So the question is find V which travels from the point A to the point B, find the components of that vector V by using position vectors. So go ahead and pause the video, give this an attempt. Once you have a solution, or if you get stuck, unpause the video and I will work through the answer on the whiteboard. I'll then compare that answer to the numbers that we have for these points to show that indeed the equation that we showed a second ago does still hold true for 3-dimensional space. So go ahead and give this an attempt and we'll be right back. Okay, welcome back everyone. So we need to create 2 position vectors, one for our point A and one for our point B. So we're going to have a position vector that goes from the origin, because it's a position vector, to the point A. I'm going to name that A, and we know that A has the components that are equal to the coordinates of its endpoint. So it's equal to 4 in x, minus 1 in y, and 6 in z. We also need to create a position vector for B. So B, we know, is going to have components equal to its endpoint, which is capital B. So it's going to have 6, 8, and minus 2. So if we're finding V, and again V went from A up to B, then what we're interested in finding is a vector that's the same as saying we're going to travel in the negative direction of A, and then in the positive direction of B. So once again, if we're traveling from A up to B, which is what vector V does, that's the same as starting at A and traveling to the origin by traveling down negative A. And then once we're at the origin, traveling from the origin up in the direction of B, which is positive B. So we take minus A and add B. This is the same if we rearrange this as B minus A, which is equal to, I may need to scroll back and forth. I don't know, we might be able to fit it in if I write it quite small. It's equal to 6, 8, and minus 2, which is our vector B, minus 4, minus 1, and 6, which is our vector A. Fantastic. So if we work this out, very simple 3D vector subtraction. We've seen this already. So we're going to take for our first component, the first component of our first vector minus the first component of our second. That's 6 minus 4. Likewise, for our second component, we're going to take the second component of our first vector and minus the second component of our second. So 8 minus 1. And then for the third component of our vector, we're going to take the third component of our first vector, minus 2, and subtract from that minus the third component of our second vector. So minus 2 minus 6. This is going to give us a vector that has the components 6 minus 4, which is 2, 8 minus 1 is 8 plus 1, which is 9, and minus 2 minus 6 is minus 8. So we have a vector V, which if I rewrite this up here, vector V, which is equal to 2, 9, minus 8. Fantastic. So vector V is 2 in x, 9 in y, and minus 8 in z. And we can check this. If we look at these numbers and we know we're traveling from A to B, if we start at A, which has 4 in x, and we travel a further 2 in x, 4 plus 2 is equal to 6. If we were starting at A, which is minus 1 in y, and we were to travel up 9 in y, minus 1 plus 9 is going to give us 8. And finally, if we started at 6 in z, but we travelled minus 8 in z, so we're going to travel minus 8 in z, backwards 8 in z, that's going to take us to minus 2 in z. So we can see that indeed, if we started at this point A, and then travelled in the direction and the length of our vector V, we would indeed end up at point B. So it does still hold, for the 3D case, the exact same vector equations that we were using for our 2D case. And with that, that is going to conclude everything that I wanted to cover in this video. Hopefully you've seen that there is nothing more involved with our 3D position vectors than our 2D position vectors. The only difference is that our vector and obviously the points, they all exist in 3D space rather than 2D space. So that means we've introduced a third component to the vectors, a third coordinate on our points. But other than that, the mathematics involved, the theories involved, they are all the same. And with that, that is going to conclude this video. Thanks a lot for watching, everyone.